All right, I wanted to go over the different types of notation that we can have for work integrals. So I've got the notation we've been using so far, which are just my favorites. You are allowed to use whatever notation for work integrals you want to, as long as it is mathematically correct. But you're responsible for being able to recognize all the different types of notation. So some questions in the book, some questions on quizzes and exams might use different types of notation. Even though I really like these forms of notation, I sometimes use other forms just to make sure that my students are familiar with all of them. Okay. So just a reminder, this is the line integral along a curve C. That'll have to be piecewise smooth, of course, for this to work. F dotted with T ds, that's basically just force dotted with displacement. Where the displacement, the unit tangent vector, gives me the direction, I scale it by a small change in arc length to get the right magnitude. Okay. This tells me exactly what I need to do in order to actually evaluate it. I parameterize my curve, and then f becomes f at r of t, so I'm expressing it in terms of t instead of x and y, or x, y, and z if we're in 3 space, and I dot with r prime of t. Remember, when you're integrating ds and you switch to integrating dt, there is always a scaling factor. And that scaling factor is, for line integrals, the magnitude of r prime. I don't see that here. That's because t, my unit tangent vector, is just r prime of t normalized. So when I switch from my ds becomes the magnitude of r prime of t dt, that scaling factor actually cancels. So the scaling factor, it's not that we forgot it, it's that it was there and it canceled. When we switch from t to r prime, we're canceling out that scaling factor. Okay, so other notation that you'll often see is that work can be the line integral along C of f dotted with dr. Now obviously, if this is going to be the same thing as this, dr should be the same thing as t ds. And it is. If you remember, when we take the derivative of a curve with respect to arc length, which is what s is here, we get the unit tangent vector. If we're using an arc length parameterization, that doesn't change the direction of the derivative, but it ensures that the derivative will always be a unit tangent vector. So essentially, this is just rearranging this to say dr is equal to t ds, very much like when we do a u substitution and we say du by dx is equal to u prime, du becomes u prime dx. So it's a very similar thing. Okay. I like this version of it better because that reminds me exactly how I got the displacement vector. This is still just force dotted with a displacement vector. This just sort of spells out the direction and the magnitude of the displacement vector. Okay, so we can have that. And then you'll also see that dr is sometimes written in terms of components. So this is like a vector differential, and its components are real differentials. So dr is equal to dx dy if we're in R2, or dx dy dz if we're in R3. Okay. And if we're going to use this notation, usually we would write f in terms of its components as well. So let's suppose that my force field f of xy, let's just say it's f of xy, comma, g of xy. So all I've done is I've given names f and g to the component functions of my force field. Okay. Now I'm doing an example in 2 space. Obviously, if I were in 3 space, there would be a third component for the z value of that force field. So then if I have this, the integral along C of f dotted with dr becomes the integral along C of f of xy, g of xy, dotted with dx dy. Now if I work out that dot product, that becomes the integral along C of f of xy dx plus g of xy dy. Now, if this is the first time you're seeing this notation, it looks kind of strange because we're really used to having an integral with respect to one differential, not this sum, okay? Of course, to evaluate this, I'm going to ultimately do what I always do, which is, since it's a single integral, parameterize things in terms of t. I'm going to switch everything over to integrating with respect to t. So this dx is just a multiple of dt. We've got to figure out what the multiple is. Dy is just a multiple of dt, not a constant multiple necessarily. It could be a function that's a multiple that I'm multiplying by dt. So all of this does become just one integral with respect to t. Okay. When you first see this, unless you've encountered it in other classes, it does look kind of strange. I'm going to just remind you, though, when we worked with differentials, if I had z equals f of xy, we defined the total differential dz to be the partial with respect to of f with respect to x times dx plus the partial of f with respect to y times dy. So we got a sum of a function times dx plus another function times dy, which is exactly what we have right here. Now, if f and g happen to be the partial derivatives of some function, then what we're integrating here is just the total differential dz. So there are some contexts where this notation actually does really lend itself to what we want to have. Those of you who are in differential equations will recognize that something that looks kind of like this, a function times dx plus a function times dy, when we studied exact differential equations, if we had something like that and it was set equal to 0, we could check to see whether that was an exact differential equation. So there are times when this notation really does make a lot of sense. Again, I prefer this or this. I don't find this to be nearly as user-friendly, but any of it is acceptable notation. And in different contexts, I have different preferences for what notation I like to use. I do want to explore this notation just a little bit more, okay, because we've essentially got this thing, which doesn't really tell me how I would integrate it. So what I'm going to do is keep this up here, but I'm going to work out how I would actually evaluate this. So keeping in mind that f, we said, was f of xy comma g of xy. Okay, and then we'll have r of t would be how we would parameterize this, with t varying from a to b. So I can write the line integral along C of f dotted with t ds this way. Okay. I'm going to now write it this way so that I can see how I would actually go about evaluating this by rewriting it in terms of t. Okay. So this would become the integral from a to b of f of r of t, which would of course just become f of r of t, g of r of t. So I would do that composition with each of the components of f, dotted with r prime of t. Now if r of t would also have component functions, it would just be x of t, y of t. So r prime would just be x prime of t, y prime of t, and then dt. So this becomes the integral from a to b of f of r of t times x prime of t dt, times x prime of t, sorry, plus g of r of t times y prime of t, all of that integrated with respect to t. But notice I could break that up into two integrals if I wanted to, and I could say this is the integral from a to b of f of r of t times x prime of t dt, plus the integral from a to b of g of r of t times y prime of t dt. Now if we compare these, the line integral along f of xy dx. Now I've written this as essentially one integral. It would be perfectly correct if I wanted to rewrite it as a sum of two, integral of f of xy dx plus the integral of g of xy dy. This, I write my integrand f using this function composition to express it in terms of t, and I can see dx just becomes x prime dt. Here I write the integrand g using my function composition to express it in terms of t, and the dy simply becomes y prime dt. Okay. So if you see something where you're integrating with just x or just y, you can use that to convert to integrating with respect to t. Okay. I think what we'll do is stop this video now. In the next example, I want to work out an example of an integral that's given to us in sort of this format and show you how you can deal with the notation. Some of you might be very comfortable with this notation, and some of you might prefer to move it back to the other notation, and I'll show you both options.